close. Excel's looks better because it's got color and it's got words and you know what you're looking at and it's nice. So what you've got right there is a curve versus a line. It's now off. There we go. But that's something we can now work with. And this, I think this only takes you to about page 2 of your booklet, because I think the rest of your booklet is how to run the regression, how to get the best fit line. We're going to ignore the best fit line. But not right away. I want to make sure you understand why we're going to ignore the best fit line. So over here, what I've started with is, I've gone back to our overriding goal of mathematical modeling, which we started back on day 2. I mean, honestly, that's where we were at day 2, was mathematical modeling. At that point, we started playing with data that we either generated or found that was linear. Actually, Brittany, remind me, I rewrote the Excel thing for the golden ratio for you after class. I can show you in 30 seconds. Cool. Yeah, we actually came in a little bit under, but damn close though. Anyway, all the data we looked at up till that point looked kind of like this. Now, I don't think we looked at any data, at least in class, that went like this. It's kind of like a horror film, I apologize. But, I mean, you could have just as easily done that with decreasing data. Okay? But the idea is, these little residuals, those little off points, are fairly consistent as the line goes down or up, whatever it is. It could be a horizontal line, could be a vertical line, could be any kind of line. But the idea is that it's got this beautiful constant, as Amber told us, constant rate of change. The idea is the constant rate of change. Now, in case you have a hard time believing that on the bike data, what I did over here was I took the data here and dropped it down to here. Now, I did do something a little bit special. I took the data, and instead of having the seconds jump from 0 to 3.4 to 4.7 to 6 to 6.9, I smoothed it out and go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll show you how we did that in a minute. There's a little bit of mathematics that we're kind of in the middle of doing, but I jumped the gun a smidge to get a point across. This is how much distance I would have traveled over those time periods. Now I know it looks a little bit weird because it says 0.6 at 0 seconds. That's the result of the best fitness of the curve. So what I've got is, I'm at 2 feet after a second, 7.8 after 2, 18 after 3, 32.6 after 4, and so forth and so on. About 213.3 after 10, and so forth and so on and so forth and so on. So what I did first was I calculated my slopes. So I said, okay, let's check what's called the first differences. That's this minus this, 1.4. This minus this, 5.8. This minus this, 10.2. This minus this, 14.6. What do you notice about these numbers, friends?
Increase.
Say that again.
Increase.
They're increasing, aren't they? Why does it make sense if they're increasing?
Is it exponential?
Be more general, Christina. I love that, by the way. Thank you. I love that.
That's just from my psych.
No, good for you. Good for you. But it's increasing. How come? Think more big picture. Brittany?
Because your distance is increasing by the seconds.
And why is that again? Because gravity's pulling me down the hill. That, right? I was looking for a bigger picture. Not a mathematical one yet. You guys are great. You guys are awesome for mathematics. What's pulling me down the hill is gravity. And since my momentum and my velocity are increasing, it's a function of gravity. So hopefully this makes sense. That I'm covering more distance each second that passes. The first second I only covered, what, a foot? That's completely understandable. If I let go of the brakes, and a second passes, I'm barely rolling. But then I keep rolling and keep rolling and keep rolling. It's like with those runaway truck ramps at the bottom of those big hills. Because if those brakes give out on that truck and they can't mitigate their speed, and it's 5 miles downhill, how fast are those trucks going? Yeah, ridiculously fast. You want to get them off the road safely. So anyway, the first differences, therefore, are increasing. But what's very interesting is, if you look at what are called the second differences, which would be do the same thing, but do it here. Look what you get. Look at that. How crazy is that? Now, they're not perfect. They're not perfect, but they are damn close to perfect. They are damn close to perfect. And when these second differences come in that close, It's actually not exponential. That isn't the best fit. We'll get to that too, I promise, because exponential explains things like where you should invest your money. I mean, important stuff.
Right.
But this, when the second differences come in this close, it's not exponential growth, it's then quadratic growth. Yeah, this is a quadratic. That's what I want to start with this next bit of modeling. Yes. Oh, it's totally rad. Totally